Hello, and welcome to the ninth in a series of seminars, webinars that are celebrating the 100th anniversary of the Institution of Chemical Engineers. And you will be able to find this one, but you can already find the other 8 webinars on the ChemEng Evolution website, www.chemengevolution.org. And all of them explore the contribution that chemical engineers have made now and have made over the last 100 years to creating a better world. And I have looked at a number of them, and I'm sure you will enjoy them if you do too. My name is Colin Brown, and I will be chairing the webinar today. I'm a materials engineer by background, although my specialism was in the mechanical behavior of materials. But like all professional engineers, I have an interest and need to have an interest through my professional registration in the sustainability and the societal benefit of the work that I do. My plan today is to engage you, the audience, as much as possible in the discussion we're about to have. And you'll see on this side of your screen, you will hopefully see a question tab, and one of the few options you have is a question. And if you click on that grey tab, underneath it, there will be a drop-down box which will say, enter a question for staff. If you type over that enter a question for staff, I will see them, they'll come to me, and we will add them into the discussion. It is important that you do that for 2 reasons. One is that we then have a discussion rather than you listening to people, but also it allows us to focus the areas of what we're doing towards the things that you're specifically interested in rather than not, of course. So the topic for today is the overall negative impact we are making through the choice of materials, particularly steel, cement and plastics. And that impact could either be through the emissions and waste products from their manufacture, or it could simply be the exhaustion of a finite resource that is the fact that we're on a finite planet. Neither of those ways forward is sustainable. Unfortunately, everything is made of something. And if we continue as we are, we risk not only causing pollution through the material use and indeed climate change, but ultimately running out of reserves if there are no viable substitutes. So as we explore today the changes that are necessary, I expect that the discussion will go towards those areas where we can expect the free market and the technologists to lead on the change, but also including consumer behavior leading on the change, and those areas where we're expecting governments to intervene through legislation. The former is easier. The market change, the consumer behavior is somewhat easier in that the free market takes over, and either cost or quality or control, lead times can drive that demand. If you say everything has to be down to legislation to drive the change, then it's typically harder because it imposes restraints on industry. They tend to be resistant to it. It may well increase cost, slow down delivery, or reduce quality. And it becomes a political decision that often needs international collaboration too, which can be quite difficult to achieve. So it'll be interesting to see that balance between the way in which we as engineers can drive this change and the way in which we then rely on people who are not engineers often to drive that change. So we've got about 90 minutes overall today for our work, and we're going to start with 4 presentations to help our thinking and then move directly to that discussion that I've described. Please therefore do enter your questions and comments starting almost as soon as you like now, so that we get those and we can blend them into what we're doing. It is now my pleasure to introduce therefore our 4 speakers in reverse order. The first person I'd like to introduce you to is Professor Fang Xie. Professor Xie is from Imperial College in London, and she's published over 80 peer-reviewed articles with a particular emphasis on plasmonic and nanoscale properties for enhancing devices for healthcare and energy industries. She's internationally known for her work in enhanced device performance, including sensing and solar energy harvesting. She would be talking to us today about her work on graphene and on metal organic frameworks. So that's Professor Xie. The next person is Dr. Leon Prentice. Hopefully Leon is with us. He is the Chief R&D Officer for SDI Limited, a biomedical materials manufacturer in Bayswater, Australia. His role at SDI is to lead on exploring new technologies and new collaborations as a way of bringing products to market. He will be talking today about sustainability in biomaterials. Thank you, Leon. The third person is Professor Paul Fennell. He's the Professor of Clean Energy from Imperial College in London. Paul is hopefully there. He will be taking on the rather large role of introducing us to decarbonisation of both steel and cement. There we are. Hello, Paul. Thank you. He's published widely and has been an advisor to the UK and EU governments on decarbonisation in particular and in green investments more widely. We're going to start our presentations, however, with Joe Bailey. Joe is a project manager at Progressive Energy Limited, where he focused on reductions of carbon emissions across industry, especially in transport and heat sectors. His current work is on the supply and use of hydrogen for novel applications. Prior to this, however, he spent a number of years looking at plastic waste stream treatments and what we might call hardcore chemical engineering to produce valuable raw materials through recycling. His talk today is called Plastic, a life-changing material requiring a life-changing future. Over to you, Joe.
Do that. Thank you, Colin. If you just confirm that you can see the presentation so I know everyone else has it, that would be great.
Yeah, we can see the presentation.
Yeah, lovely. Thank you, Amit. Okay, so yeah, plastics, a life-changing material, but one requiring a life-changing future. And I think there's a good debate to be had about whether plastic is a miracle material or a menace. Although I would say in society that generally people are more gearing towards the latter. If you look at these two pictures in the top left, almost everything in that picture is made of plastic, and modern medicine would not be able to cope without use of plastics. The fact that it's relatively cheap to produce, it's lightweight, sterile, all the amazing different properties that different forms of plastic have make it essential for carrying out those activities. In contrast, in the bottom left, you'll see the huge problem of plastic waste, the fact that it doesn't degrade, at least over short time frames. In fact, what you see there is two young boys doing a form of mechanical recycling, so searching through the plastic soup, trying to find specific types of plastic that they can earn some money for through mechanical recycling. And over the last 100 years, the growth of plastics has really been astronomical. So it's really infiltrated almost every area of our lives, from transport to goods, healthcare, construction, but the main source of growth has been plastic packaging, which you'll see in the kind of bottom blue bar of the charts, and that's really continuing to drive the growth as well going forward into the future. So there are different types of plastic. Generally, there are 7 different groups, and some of these you will recognize. If you have plastic goods, it will often indicate the type of plastic that it is on those goods. But not all plastics are the same, obviously. They have different properties, but also kind of different recyclability potential. The precise ability to recycle will vary in area, and it's also different with different technologies. So whereas some plastics can be easily mechanically recycled, others can be chemically recycled, and sometimes just because something can be chemically recycled doesn't mean it can be easily mechanical recycled, and vice versa. As a bit of a general take, PET and HDPE, there are established commercial operations for recycling these materials, and they typically have a value. There are then materials like LDPE, so low density polyethylene and polypropylene, where there's a developing market in areas you will be able to recycle these materials, but not everywhere. And then there are a group of plastics where really there aren't kind of commercially operating examples of these materials being recycled. But the overall picture is pretty damning. So looking at that 2-litre bottle on the right, you know, over the course of history, the majority of plastic has been accumulated in landfill or dumped and littered into the environment. A very small percentage of that has been recycled. And actually, when we talk about recycling, often people are talking about recycling into lower grade products. So it's not genuine bottle to bottle recycling, which is an even smaller percentage. In terms of what the future picture looks like, so the growth of plastics is just expected to increase on those curves that we saw on the first slide. So by 2050, we're looking at 4 times as much plastics production. We're also looking at a higher percentage of oil being diverted into plastics production as we move away from, say, oil for transport methods. And that also means that plastics will take a greater share of the overall carbon budget in society. The issue of pollution is obviously hoped to improve, but we would be looking at current rates of as much plastic in the oceans as fish, which is a quite depressing outlook for 2050. So how can we imagine a different world, a different use of plastic? So firstly, regulation of plastic use and plastic disposal has been shown to work. So in that top graph on the right, you will see recycling, energy from waste, and landfill disposal of plastics for different European countries. And what you see in the group of countries in the yellow block, those are all countries who have active policies against plastics going to landfill. And you see that as a result, plastic recycling and energy from waste is increased. So regulation is an important metric to use. But we're also going to need new technologies. So looking at the picture on the bottom right, about 20% of plastics can probably be reused. About 50% can be recycled. That will need technology development. So in new chemical feedstock recycling techniques, such as monomer recycling. But there is also a great deal of sort of fundamental redesign required. So some of those plastics that don't have identified technologies for recycling, or where we're using mixed materials in products, how can we move away from those, replace them with alternatives? I just want to finish my presentation with a bit of a busy slide, but just to really get the message through of what a future net zero and circularity scenario could look like. So this is taken from a report by a company called Systemic. Highly recommend reading the report if you have the time, but it really looks at the fact that to solve the issue of plastic pollution and also the climate impact of plastic generation, we really need a complete supply chain rethink. So it's not just focusing on the production of oil and gas out the ground, but it's really thinking, how do we eliminate and reduce the amount of plastic we're using? How do we substitute it where it makes sense to substitute it, either with plastic alternatives or other material alternatives? How do we design for recycling? So in the fundamental product concept, and then how do we increase mechanical recycling capacity and scale up chemical recycling? So the size of the prize is huge. So if you look at those figures at the bottom, you know, the number of jobs that we could create, the number of emissions saving, the reduction in plastic waste in terms of coming from virgin materials as well. And we're talking about a quarter of the current capital deployed in kind of chemical production being redirected to low carbon technologies. So whilst companies are doing a lot to increase plastic recycling rates, it's still dwarfed by the amount of investment in kind of virgin chemical production from traditional methods. So a lot more is needed in this space. Thanks, Colin. I'll pass back to you.
Don't go too far away, Joe. I'm really struck by what you said there about very soon there'll be as much plastic in the sea as there will be fish in the sea. And then in your last slide, you talked about the supply chain needing to change. When do you think you will get to the point where we're harvesting plastic from the sea?
Yeah, it's interesting. I mean, one of the, I guess, great things for the topic of plastics, perhaps different to CO2, is it's potentially easier to take from landfill to take out of the ocean. There are obviously some challenges in terms of contamination, so biological matter and things that can get into it, but the fact that you could take it out the sea and then still recycle it is a huge plus point, and something that allows us to make a kind of change in the future.
I'm just feeling that the things I've seen on the television to now are more about sort of cleaning up mess near the coast where people can see plastic bottles floating. They're not actually going into the vast bulk of the ocean or wherever the plastic is. They're almost too cosmetic or something, that actually mining the ocean, boiling the ocean, is going to be quite that's a big challenge, isn't it, when you say change is necessary?
Yeah, I mean, there are some interesting companies who have developed techniques for taking plastic out of the wider ocean. The waste actually accumulates in particular places as well, to do with kind of the currents and where it takes it from. So there is work being done on that space to try and take plastic out of the environment once it's emitted. The other thing is worth noting, the overwhelming majority of plastic leakage into the environment occurs in a very small geographical area of the world relative to the wider world. So it comes from a series of rivers, predominantly in Asia, where most plastic leakage occurs, and actually targeted waste collection infrastructure in those regions could make a massive difference. The slight counter argument to that is a lot of the plastic waste being emitted there is coming from the rest of the world and effectively being shipped there, and then due to lack of regulation, lack of waste infrastructure, being leaked into the environment.
But thanks very much for that, indeed, Joe. I think that I'm feeling some parallels there with our next speaker, of course, when we get to ideas of carbon capture and storage. Actually taking it from situations where carbon is produced is, on the first case, quite often easier than just going to try and boil the ocean to try and find the carbon.
Yeah.
So thanks very much, Joe. And now we move to Professor Paul Fennell. Paul, hopefully you're there with us. Paul, as we know, has been very active in policy work on decarbonising, including carbon capture and storage. And his CV shows that his work is very acronym rich, including such lines as Paul has conducted techno-economic analyses, including consideration of the no-folk cost of novel BECCS systems as part of the ETI TESBIC and TESBIC 2 projects. Reassuringly, however, Paul is also an acknowledged science communicator. And so, as well as learning what that lot might have meant, we are sure we treated a great overview of the state of the art of decarbonising steel and cement. So, Paul, over to you. Thank you very much.
Paul, just to let you know that we can see your presenter view at the moment, so you just need to swap your slideshow and presenter, and you're also muted. That's great.
Right. Can you see me? Can you see the screen now?
Yes, perfect. Thank you.
Excellent. Thank you. Apologies for that. Right. So talking about decarbonisation of iron and steel, and then I'm going to talk a little bit about cement later. So there's three main ways that you can make iron and steel. You can either go the blast furnace route, the sort of old school, lots of coking coal and lots of different CO2 emissions at different parts of the process to make pig iron, and then go for a basic oxygen furnace, and then you've made your steel. You can go for a direct reduction method. So you take your iron ore, and instead of using gases from coke to rip the oxygen from your iron and steel, sorry, your iron ore, you can use either natural gas, or a lot more prevalently now, at least being proposed use hydrogen to reduce your iron oxide. Then that goes through a bit more processing, probably into an electric arc furnace, and then you make your steel. And the alternative is to do recycling, which obviously is the best solution. But you know, we still need to increase the amount of recycling that we do. So the enabling technologies to allow decarbonisation through the different ways that are discussed here are, for the blast furnace, you need CCS. Really, you're producing CO2 as an intrinsic part of the chemistry of your process here, so you need CCS. For direct reduction, you need cheap hydrogen. Somebody needs to be producing a lot of cheap hydrogen for you. And for electric arc furnace, you need cheap and decarbonized electricity. So iron and steel is currently around 7% of global CO2, and around 30% of the primary production, oh, sorry, that's secondary production. Around 30% of the production is from electric arc furnaces, recycling, and a very small proportion, maybe 5%, from direct reduction. But there's huge potential for that in the future. The remainder comes from blast furnaces, and the key problem is that there's been huge progress with blast furnaces in the last few years, 61% energy reduction since the 1960s, but that means that further improvements are challenging and are now running at only 0.4% per year. So down here you can see the different emissions, and this one's a bit controversial, so it's probably a little bit more than that. So blast furnace produces quite a lot of CO2 per ton. DRI, this is with methane, not with hydrogen, about 0.7 tons of CO2 per ton. And then electric arc furnace, if you've got a decarbonised amount of electricity, doesn't release very much at all. So decarbonisation is challenging for the blast furnace route. You've got a lot of different emitters on a steel site. You've got the blast furnace, you've got the basic oxygen furnace, the sinter plant, on-site power, etc. So you've got many different sources of CO2, and so it's not like a power station where you've got one smokestack and you can just try and capture the CO2 from that, and that's difficult enough anyway. But here you have the possibility of using CCS on the majority, but at some cost. It's important to note here, though, that 74% of EU steel blast furnaces are requiring refurbishment by 2030. Now that means that if we are going to do something, we need to get CCS on those when they're being refurbished, because refurbishment goes on every 25, 30, maybe 50 years. So if we miss the boat here, we're somewhat challenged. Right. Direct reduction of iron can be used with hydrogen, but the trouble here is that when you do a back of the envelope calculation, you'd have to about treble the amount of hydrogen that's produced on Earth if all of the primary steel making was switched from blast furnace to direct reduction with hydrogen. And the hydrogen eventually needs to become green. And at the moment, unfortunately, it's around 2.5 times more expensive than blue hydrogen. So blue hydrogen, which is hydrogen with CCS methane that's been reformed, and there's CCS on the plant. So carbon capture and storage being used on methane to produce hydrogen. The electric arc furnace is a very good solution, and you can work with the direct iron for primary steel production, but it does need a lot of electricity. So some of the new things that are coming around, there's a lot of people who will tell you that they can directly reduce the iron oxides via electrochemistry using renewable energy, and there's been work in this area for quite a few years. It's challenging to do it, and there's a variety of entrants into the market. Some have more or less technical information available for you to actually look at, and caveat emptor. Hydrogen DRI, SSAB in Sweden delivered the first CO2-free steel to a consumer to a customer, the Volvo Group, and that was via hydrogen direct reduction as part of the hybrid project. There is a commercial plant at Al Rayada, and it's the first commercial CCS on steel. It's producing it's capturing 0.8 megatons of CO2 per year, and slightly unfortunately, it's then being used for enhanced oil recovery, which means that its environmental credentials are a little bit less good. Although, in fairness, it does mean that their profitability is much better. Now, this is the what used to be the future of steel. It's the Hysana process. Tata here is demonstrating what was a novel smelting reductor. It was demonstrated in 2018, and they're currently decision pending for a large-scale plant in India. Hysana was the future of steel making until about 3 years ago, when DRI and hydrogen became the future. Basically, the costs of hydrogen have been plummeting, so people are thinking more about using hydrogen in the future. I do worry, though, that this relies on people from in the future having very, very cheap hydrogen, and there's some limits on how cheap hydrogen can actually get. So I think you should keep the world should keep the CCS options in there, as well as just direct reduction of hydrogen, or direct reduction of iron ore with hydrogen. So that's me. Do you want me to go straight on to cement, or do you want to have a break, have a chat, ask any questions, or shall I just bang on?
Paul, I think if you just go straight into cement, that's absolutely fine. There's a tremendous amount in all this, I do realise, but let's have the cement, and then we'll pick up one or two of the themes quickly from both of them together.
Okay, so cement, you have two main sources of CO2. You have the precalciner here, which is where limestone, which is the major component of cement going in, the major feed to the cement plant. And that here, you go from calcium carbonate to CaO plus CO2. Issue here is that that's fundamental to the process that you actually, the chemical reaction there is fundamental to the process, and that produces about 60% of the CO2 emissions from cement. Then you go into the kiln, and then you add some silicates. Basically, you add some clay to your system, and then you work. It goes through a big old rotary kiln, and comes out as cement, and then you do a bit of post-processing and that sort of stuff. The fuel emissions are about 40% of the process, and you can actually do some things with those, but the challenge is that bit. Right, about 6.5% of global CO2, and cement clinker is the product of the cement kiln. So that's what comes out from the kiln here, and then you add in extra bits here. It's the glue that holds concrete together. So that's the good stuff. That's the stuff that you need. And the majority of the emissions is from the intrinsic chemistry of the reaction, and the fuel is responsible for the remaining emissions. Now, a busy slide, but all I'm saying is that the CO2 that's emitted, yes, I can put the laser pointer, there we go. The CO2 that's emitted is a combination of those process emissions, the emissions from the limestone, and the fuel, less any CO2 captured, less any CO2 that's set off because you're using biomass. And then interestingly, when it's set in place, concrete actually reabsorbs CO2 over a period of time. So you get about 10% of the CO2 that's emitted, and depending on who you talk to, more, and depending on what you do with it, more at the end. But there's quite a lot of reabsorption of CO2. So what does this mean? Well, here's a number of different graphs for a cement plant, and I'm putting on carbon capture and storage from 0 to 1. So basically 100% capture of the CO2, which is maybe a little bit ambitious. Maybe we should be thinking about 90% up here. And a variety of different treatments here. So here we're potentially using less clinker, et cetera, et cetera, et cetera. And this is the CO2 emissions relative to the baseline, right, on this axis. And what you can see is that if you're running your plant on coal, you have to do a large amount of CCS in order to get anywhere near CO2 neutral. Hydrogen, you get rid of those fuel emissions, but you still need to do quite a lot of CCS because you've got the process emissions, which you're not treating. And then the important ones here are the fact that if you've got biogenic materials, if you've got a fuel with a high proportion of biomaterials, such as municipal solid waste or such as biomass, you can actually drive by capturing the CO2 from the exhaust of the cement plant. You can drive the emissions negative, and that's actually a really quite useful thing to be able to do in the models. And that's also a useful thing to be able to do because this is a massive scale industry that is currently operational, right? So everybody talking about CO2 capture from the air, that's great, but this is an industry that's already available at scale and just needs to see CO2 capture on it, which I will grant you is hard. So what's going on? So Lilac and Lilac 2 is a successful project using a new type of calciner with integrated CCS. So basically, the CO2 capture is intrinsic in that. Essentially, it's a big hot tube which you drop your limestone down and you fire externally, so the limestone never actually sees any nitrogen from the air, and basically you produce a pure stream of CO2 intrinsically. This is the Lilac 1 demonstration, which was about 13 stories high, and it was successfully demonstrated. I was actually a part of the project, but then they went on to Lilac 2, and it was deemed that British members of the European project would be a bit too much of a risk, so thank you, Brexit. And it's now being demonstrated at a scale of around 20% of a cement plant in Lilac 2 as another EU project. Norcem Brevik is looking at putting amine scrubbing on around 40% of the plant, and it's currently in design. So this is the biggest demonstration in the world, the Norcem Brevik demonstration, and that's straight amine-based carbon capture on the end of the plant. There's a variety of reasons why that's not a brilliant idea, but I'm not going to go into them. Common issues between iron, steel and cement and other things. Basically, if you look here, here's the cost of CO2 avoided, and here's the cost for a variety of different industries. And you can see that different technologies are uniquely useful for different processes. So up here, you'll see amine scrubbing applied to cement, extremely high cost of CO2 avoided, but calcium looping or oxyfuel should have a much lower cost of CO2. And then down here is where we should be starting, which is all of the high CO2 concentrate, the streams, the processes which produce a high concentration of CO2 at the end. And then you can see that depending on what you do, iron and steel and refineries are also quite expensive. Key for any manufacturer is fair competition between regulated and unregulated markets. So a carbon border adjustment, which means that steel or cement coming into a regulated market, a market with a cost of CO2, needs to have some sort of cost adjustment. Otherwise, the industry will just be offshored, and you know, our CO2 emissions will just be offshored rather than being cut. And you can do a variety of different things. And when we published something that said that you could how you would decarbonize a skyscraper, and you know, you can use less of the materials. We can currently use far too much iron and steel, far too much steel and cement when we're building things. Codes are challenging. We can switch to directly reduced iron, we can change our fuels, and we can do CCS. And importantly, the cost of decarbonisation of the raw materials is tiny in comparison to the cost of the building. So people sort of saying, oh, you know, this stuff's going to be very expensive. Well, the raw materials in a skyscraper are negligible in comparison to the finished cost. And thank you very much.
Well, thank you, Paul. And if anybody's got any strepsils, I think does Theresa May have strepsils? It'll be very. We're going to come back, Paul, I'm sure, to hydrogen because Joe Bailey, our first speaker, would have been champing at the bit. I'm sure when you said that hydrogen's going to always be expensive and difficult to get, or whatever you might have been inferring, and certainly a number of these environmental impact things seems to me to be all about, oh, if only we had infinite amounts of low-cost, zero-carbon electricity and infinite amounts of low-cost, zero-carbon hydrogen, the world would be quite different to the one it is.
Yeah,
so
we haven't even got enough high-cost, CO2 expensive natural gas at the moment. So you know, we're going to be in trouble.
Yeah, so I'm sure we'll come back to that because it's a bit like somebody trying to lose weight or something, isn't it? You say, oh yes, well if only there's a, yeah, but it's not going to happen, is it? we are kind of where we are. The question I've got for you is this bit that you mentioned right at the end there about border controls over countries that are taking an interest in this and countries that are not, and then the offshoring that might occur. Do you not see a significant barrier to that as being the creation and certification of a system that establishes what the carbon is in these things? Because it's so much as whether governments want to control it or not, we'll have a big debate about, oh, mine's not as bad as you say it is.
Yes, I mean, it's a potential problem, but I mean, there are steps being taken in the EU at the moment, and I'm sure that we'll just copy the legislation to actually set in place, you know, traceable CO2 standards for major companies. I mean, major CO2 emitters. Iron and steel and cement are certainly coming under it, and they are looking at how to do border adjustment very carefully because, as I say, the EU wants to protect its lower carbon industries from high carbon things coming in from abroad. So yes, I'm sure it's going to be something that we'll be arguing about at the WTO for years, but it's not an insurmountable problem in global trade. I mean, it's things have to be certified for all sorts of things. Chemicals need to be certified to be tradable. You know, you have to show that you've produced them in accordance with the regulations, etc. So this is just one extra regulation that you would add on.
Right. Do you think there might be a role for the Institution of Chemical Engineers there, Paul? I mean, some sort of independent-ish body?
Yeah, I mean, I think it certainly, I mean, with all the sorts of things like, for example, the green taxonomy, what is required in order to claim that your investment is green and therefore can be issued a green bond. The members from the ICME have been helping out with developing those protocols. There is a role perhaps for the ICME, but it's going to have to be, a global effort. So, the Yanks are going to be coming in as well, and I'm sure the EU will have its view. So it'll be by negotiation all around the world.
Yeah, thank you so much, Paul. But I do remember a little bit about how complex this all is, because people criticise, for example, India for the amount of emissions it makes in making some particular product, and they answered to us saying, "Ah, yes, but all our workers cycle to work." And in America, everybody drives to work in a large gas guzzling car. I hope you're taking that into account when you're telling me what the embedded carbon is in my product.
Well, the big thing is China. I mean, everybody bangs on about the fact that China produces large amounts of CO2, but who are they producing the goods for? I can go and find my iPad and these sorts of things, and we can talk about where the emissions actually happened, but the physical thing is here, is for me. So I'm not going to tell China off too much for emitting CO2 for me.
Yeah,
But
well,
maybe
I
we
was going
should
to say
work
mea
to.
culpa on that one, Paul, because you did do caveat emptor, and I introduced you by suggesting that you would have lots of acronyms, and we'll just move into Latin as to the solution. So thank you so much for that, Paul. If you could stop sharing your slide, Gareth does that, and we will now move on to Dr. Leon Prentice. And Leon, we met just briefly before. He's a fellow of the Institution of Chemical Engineers. He's based in Western Australia. And in addition to chemical engineering, he holds qualifications in physics and in, as we'll see today, biomaterials. He has chaired Engineer Australia's Chemical College, as well as serving on the Economies Learning Society Committee. He's introducing us today to the challenge of sustainability in biomaterials under this rather challenging title of How Customization, Clinical Application and Regulation all make it more difficult. So over to you, Leon. Thank you very much.
Appreciate it. Hope you can see all my slides. Yeah, and I guess maybe let me start by saying I feel a bit behind the 8 ball, because biomaterials is one area where I think we're a long way behind in thinking about sustainability. But that said, I also want to say that this is very much a personal passion for me, and I would love to see these areas come together. I spent a lot of time in sustainability, and I was pleased to win the IChemE Sustainable Technology Award a long time back in 2011. That was for magnesium, not for biomaterials, but I would really love to see real traction and seeing a difference made in this area. Let me also start by connecting a couple of threads. Joe's opening slide with the medical surgical practice going on really brought this home. There's a lot of overlap here with plastics. And Paul's presentation talking about the involvement of codes and regulations is something that you think that you'll see a great deal as we talk about biomaterials. Now, let me start by giving a definition, because I think there are 2 things we could be talking about as we do this. So I'm going to be talking about biomaterials as that substance, that engineering form, which is intended to go into living systems, that is biological applications of materials. And this covers a wide range of materials. We could cover everything from ceramics to polymers. Think, hip implants are often both. Metals, anything. If you've had a stent or a hip implant or screws put in you, bio-derived and synthetic materials. It can include hybrid materials that are one type and another. They can be inert, they can be integrative, they can be resorbable. For example, magnesium alloys that then disappear into the body. They can be active and even include live cells. So it's a very, very big field in terms of the breadth of materials that we're talking about, but it's also very highly procedure or application specific. So it's very highly regulated as far as that goes. And these materials that we're talking about are generally for specialized clinicians' use. I'm not really talking about the Band-Aids that you'd use at home, though they can be thought of as a biomaterial, if you really want to put it that way. But they generally go to hospitals, dental practices, other areas like that. I will note that when a lot of people talk about biomaterials, they also mean bio-derived materials. Now that ends up being another whole big discussion. Tree sap glue, wooden houses, beeswax candles, even the paper on which you take your notes could be considered as bio-derived materials, but I'm not talking about that as much. I'm talking about the biomaterials themselves. So big trends. To be blunt, that the high margins in this area reduce that pool of sustainability. Most of the value is in the effect and the technology itself, not in the cost of the product. Right? If you go and get a stent put in because you've got, I don't know, and you've had a heart attack and you really need a stent, that stent itself is going to cost somewhere between $5,000 and $10,000 pounds, right? the actual weight of it may be only 1 or 2 grams, right? So that the pull of sustainability you can even see from that is not there in the material itself. It's about the technology, what goes into it. It's also, and this is a big topic, the increased regulation makes sustainability very complex to handle. And you can think of this at the start, the middle, and the end. Right? So at the start, all your ingredients are highly regulated, everything. Right? I had a case in my workplace where we were changing a raw material from something to something almost identical. And the effort that went in to justify making a switch from something that's essentially the exact same chemical composition and structure and form is so complex. And if you start using natural ingredients, say, for example, an extract from a plant or a natural honey or something, it gets that much complex again. In the middle, there's all this regulation around the in-process control, the rigidity and the validation. The company I work for is in the process of gaining accreditation through the new EU medical device regulations. And that process is so complex that everything is nailed down. Every signature, every amount is double checked. If there's a variation in the process, you can't change it. Similarly, the end of life, the biohazard disposal and processes, there are very significant reuse limitations. You can imagine, even if you go to a hospital, you don't really want to use something that's being reused, recycled without very significant processing and checks along the way. The other tricky bit is often limited shelf lives. So those vascular stents I mentioned do have a shelf life, and I've worked with hospitals here in Australia where up to half of what they buy ends up going to waste without actually going into a patient, right? Because it's either past shelf life or they show up to surgery and open a packet and it's a different one from what they intended to use, that goes to waste. So it's complex because it's all regulated. And systems are becoming more complex, not less, particularly in a few ways. One is that the patient-specific solutions. So now if you go and you're going to get an implant, there's a whole lot of 3D printing around that, right? If you 3D print a patient-specific implant, obviously you can't reuse it. The recycling process gets complicated. I could tell a funny story about a crematorium and some titanium, but might leave that for question time. The other bit that's more complex is embedded electronics and sensors. So nowadays, if you get a pacemaker, it's got things built into it, right? Is there a recycling option for that? Is there a sustainability option for that? You can see how it's more complex. And in particular, as soon as it starts linking in with patient data and privacy implications, it's more complex again. So all of that probably sounds really, really depressing. This industry is really, really bad at sustainability, if I can put it that way. It is poor. There are a lot of things that we can do, but the road is long and the trends are just starting. So let me give some of the avenues, some of the ideas that I think can push us in this direction further. One is the awareness. So both from clinicians and manufacturers, but also, I should add here, the pool of end users, of the patients and consumers, right? Be aware of how much waste goes out. For those who are clinicians, those who are manufacturers, you tend not to see what goes out of a hospital to the incineration. You just don't see it, right? If you're involved in a dental practice, you don't see how much waste goes out per patient. It's huge. So raising that awareness, just knowing how much goes out. I think another thing I would say is that preference for bio-derived and natural materials. So working out pathways of getting those types of materials into clinical settings is one of the real avenues towards sustainability. So even the first slide that Joe showed in a surgical practice, right? How many of those materials have come from natural sources? What are the ways that we can use less regulated materials in high demand situations. Right? What can we do with, polylactic acid? What can we do with cellulose? What can we do with silk? Right? Those sorts of questions. There is some self-organization among manufacturers. There are things like packaging covenants and sustainability initiatives. I'm involved in particular with the dental industry, and there is a global movement for sustainability on this. There's been a publication about that just this July that lists people from our organization among the panelists. We're looking at how we do that at a global scale. Another avenue that I don't think has much traction yet is early stage thinking. This kind of touches on what Joe said about the design for manufacturing. If you're starting early and you bring in the early stage thinking, I think there are things you can do. I think there are material choices you can make and process choices that can be made that actually have practical implications and can be validated for reuse. Right? So the loop between actual clinical application of a biomaterial and its potential reuse or recycling can be much tighter than the extent it is now. At the moment, it's a big step to go out to make something inert and safe for reuse and then come back. But I think that can be made tighter. Refilling is one of those. To give a kind of an analog to this, I stayed in a hotel. I was on holiday recently up in Cairns, beautiful far north Queensland of Australia. And the hotel we were staying at had pump packs in the bathrooms instead of the little bottles of shampoo and conditioner, because that's one of the things they're doing. Imagine the medical scenario having that sort of refill type of process. But at the same time, there are no good closed loop processes at the moment. Incineration is the only real current option, particularly for sterilization and reuse. It doesn't work very well. And the design needs, the regulations getting tighter at the moment don't help. They actually make it more difficult. So I think there's a call here for medical device regulations, for the FDA and the TGA, the CE, MDR, those sorts of regulatory frameworks to be able to handle variability to it. And I give that analogy with paper and bamboo and straws, right? If you're trying to gain for sustainability in what straw you use in your cocktail, there are other options, right? And those options are valid. They have their drawbacks and their positives, but they are valid other options that need that flexibility in application in order to actually be implemented. Last one for me is, I think we need those sorts of tools. I think Paul touched on this a little bit, that cradle to grave life cycle analysis. Nobody's really doing this. This is an IChemE opportunity to really think about how we quantify that well. Right? What happens when you have a biomaterial of some sort? How can we quantify better what's really been involved in its process? Because the process is long and has been complex. So how do we quantify that really well? Let me wrap that up there and see what you want to do on.
Leon, thank you very much indeed. And I had a prejudice before I heard your presentation that you were going to say it's all biohazard material, it's all sort of disease-ridden or whatever, and it's not, is what you said. So is there not a link between the fact that you need to incinerate all of your waste and Paul, who sat there waiting for his municipal solid waste in order to generate energy for his processes? Is there not a natural sort of valuable use of your waste streams as being energy sources for other recycling processes or other environmentally friendly processes?
There can be. Yep, it's a really good question. But the pathway to make something useful or reusable is kind of inversely proportional to what you're going to use it for. If you're going to incinerate something for energy, then yes, that's simple. You don't need to do anything other than dump it in a furnace, ideally, right? If you're going to do something more valuable with it, say you're going to reuse an item, then it becomes more complex to make that safe for reuse. And as components get more complex, you start needing separation processes. I mean, I think we're going to hear probably from Fang about this in terms of batteries. You've got to start pulling things apart in order to recover more of the valuable components.
Okay. Well, thank you for that. Thank you, Leon, and thank you for that segue into our final presenter, Professor Fang Shi. Do keep questions coming in for all of our presenters, including Professor Shi, who is a member of the Royal Society of Chemistry and also serves as an associate editor for several journals, as well as her own technical papers. She has filed 9 patents on her work, I think 7 of which have been granted as well, Fang. So over to you. Thank you very much.
Thanks for introduction, Colin. Can you hear me clearly?
Yes, I can.
Yeah, great. It's my great pleasure to be here. So I'd like to introduce 2 potential materials of the future. One is graphene and the other one is metal organic frameworks. So what is graphene? It's a single layer of carbon atoms with hexagonal arrangements. So carbon to carbon. So here, hold on, let me put my pointer on. Carbon to carbon distance is about 1.42 angstrom, and the graphene is the thinnest material we know so far, and it has the most amazing properties. On the left-hand side here, you can see this material's mechanical properties. For example, it's very strong and tough, and it's also light and flexible. It repairs water and corrosion. In terms of electronic properties, it has a very high thermal and electrical conductivity. And because it's only carbon in these materials, so it has very biocompatible, not really toxic for biological cells, and it has eco-friendly. So these unique properties make graphene almost can be applied in a very wide range of applications. I can say almost every single industry. So this diagram actually is from the Graphene Council. You can see graphene has been classified, used into single layer, the yellow bar here, and then multi-layers. Bulk means the graphene flakes in powder form, and they can use a lot of composite. So what we can see here is graphene has impact in more than 45 industry sectors and applications. And currently, there are over 200 companies worldwide, including graphene producing graphene and graphene application developing. And most of these companies are small scale, and I noticed quite a lot of them actually are spin out from universities. So for big companies like Samsung, like Tata Steel, Paul mentioned earlier, and they have their graphene research center. For example, Tata Steel, they established the graphene development center in 2018, and the center produced the corrosion resistant graphene pens. They also supplied their graphene powders to some famous car tire companies. And they also start developing graphene inks, which is not commercially available so far, but I think it's on the way. Here I list some very specific exemplar applications. Let's focus on cancer detection. So some cancer detection, if you use graphene on to link the positive and negative electrode, you can use this field effect, transistor effect, to enhance the sensitivity, and which lead to the early diagnosis of cancer. The other interesting material property were leading the application in concrete, for example, because graphene is 2.5 times stronger and 4 times less water permeable than the traditional concrete. So it is possible to form a composite material to replace the traditional concrete. And also their chemical structures make them excellent candidates for water filtration. That there's a lot of, I think there's industry scale there. And also they are very lightweight and mechanically so strong. So there's a lot of sport equipment. They try to blend in graphene in their product. To assess the sustainability of the graphene production, because it's at very early stage, I think we really need to have a holistic way by thinking the circular economy, even at the very beginning, rather than to tidy up later. So in this data set here, published recently, you can see the correlation between the global warming potential over the different methods of the graphene production. And CVD actually is the most common method used in industry scale. Give the highest quality of graphene. Actually has the highest GWP, and which means it's the most negative impact. And other methods like chemical oxidation and ball milling methods generate relatively mild impact, but it's really not the scale for industry to pick up. So there's a dilemma here we need to solve. What else? So clearly for the future graphene production, it needs to be compatible with the circular economy principle. And it has been reported like the life cycle assessment is an excellent tool to assess environmental footprints of the production process. As I said, this is still, in my opinion, is still an infant stage. There are many companies out there, but it's a smaller scale, and there are some branding graphene application development, but the large scale production of graphene is on its way, I would say. And the next material I would like to introduce is a MOF. MOF has a huge potential, and this is how the MOF structure looks like. You normally have a metal center and have organic linkers, and you kind of like a Lego, you can manipulate their structures by manipulate the organic linkers which link the different metal nodes. So because they are so volatile, and you can basically manipulate their pore size and their shape, and the linkers, these organic linkers here is ready to be further function chemically, to have some more chemical functionalization. Some MOFs have tunable optical and electronic properties. And like graphene, MOF has a huge, so from this kind of structure, you probably can tell the properties got very high porosity, and which induce the high surface area. And because this is naturally a crystal structure, so they have their very unique electronic properties, and their applications is mainly focused on gas storage, energy storage and purification, and some drug delivery properties applications. So here I list some examples of MOF structures, just give you a flavor of how MOF used for gas storage. So for example, MOF MIL101, this kind of structure is very specific for hydrogen and CO2 storage. And also I'd like to mention MOF 5 here. It's very specific for hydrogen storage. So this is kind of new and designed materials. At industry scale, we really need to think a true circular economy. So the producers really need to rethink the way of production goods in order to eliminate waste and continue use available resources. For example, the disposals here, ideally it should be reused and refurbishing or recycling back, and to minimize the resource input here. And on the right hand side here, I just give you an excellent example of MOF for circular economies. So you can use MOF for CO2 capture and sequestration. And once the CO2 is stored, and some of the stored CO2 can be recycled in a circular manner by converting them into liquid fuel, for example, methane or methanol. This forms a nice, again, this conversion is by MOF. This forms a very nice a circle. As I said, it's really industry scale up. I think it's still at very early stage or infant stage, and it's in progress. There are some key players in US, UK, Canada, and New Zealand. I think it's one step behind graphene industry, but personally, I feel MOF will be a very promising material to solve a lot of problems in the future. Thank you.
Thank you very much, Fang. And you've really, in your last sentence there, you've highlighted the get out of jail opportunities. I think that the technologies you're bringing to us here, saying, oh, we can now do these things. But I'm interested just initially, before we move to the general discussion, and thank you for those of you who are sending in your general questions. Before we move to the general discussion, isn't one of the challenges with MOFs and with graphene, although they can do the marvelous things that you've just described that they can do, that they're so expensive, and they will always be so expensive, that you would never use them in a steel plant. You know, Paul using it in a steel plant to capture CO2, or Joe using it in a truck to store hydrogen. The hydrogen tank on a heavy goods vehicle that's made of MOF would cost more than the vehicle, wouldn't it? Isn't there a real challenge with the kind of the cost to volume ratio of these materials?
So even those companies, the all active research companies, I mean, it is myself in my lab, we use MOF to do the CO2 reduction. I think the key thing is not just how expensive it is, even it's a research stage, it's very low efficiency. So we kind of plug in MOF into traditional oxide, TiO2 zinc oxide, to make this photoelectrochemical photocatalysis. But it has wonderful properties. We just need to find a way for the number one, mass production, and also before the mass production, I think keep in mind to form this circular economy mind, so not generate a lot of waste. I have to say more production in the lab scale, it still use a lot of organic stuff that's still polluting. I mean, the process is not biological friendly in a sense. So there's a long way to go.
Yeah, but it ought to be intrinsically more efficient than amine scrubbing of flue gases, for example, in carbon capture and storage.
Yeah, so because it's unique properties, it's useful. Yeah. So, I mean, there's a lot of questions to answer about mass production, the costing. I mean, there's a lot of things. I hope if governments like to put in some scheme to help us to develop, to go scale up. But at this stage, I can't see. I see them promising, but the mass scale production isn't going well.
Great. Oh, lovely. Thanks very much, Fang. And if I can now have all of my panel back, we've got just over 20 minutes left to take some questions. They're just coming in. Still got your slide. Lovely. The first question we've got is from Tegan Norster, who is a prize-winning chemical engineer, and she asks for me what is a very interesting question. So we've heard lots of engineering technical discussions from people here. She's got a great people-based question, and I'll ask all of you in turn here, that once you've got these marvelous solutions and they all work, what qualities do you think are needed in the employees in these companies to make this stuff or to encourage these things to happen? Do we need to have kind of diversity and inclusion as a key target for the employment of companies doing these things, in order to make sure this change happens, or does it not really matter? Does the technology really just ride over everything? Joe, let me come to you first. How important is the staff to making some of this stuff happen?
Yeah, absolutely essential. There's lots of studies out there that show a diverse workforce is the most innovative form of workforce. We've heard across the presentation the breadth of areas that need a sustainability focus with materials and the diverse application of materials. So we need a diversity of thought, we need new ideas, different ways of doing things, and employees will absolutely be center of that. I would say the other thing is these are societal topics as well. I mean, if I talk about just specifically on plastics, companies cannot do this alone. We all have to recycle goods in our home, and we all have to do that diligently and responsibly. And we have to be responsible consumers. So every person is involved in this work. It's not just the employees at the companies.
Paul, you talked about the collaborative research that you've been on for the different projects. Do you find that when you do that actually diversity helps, or really it doesn't? It's the technology that wins through here every time.
I think that diversity is really important for improving the quality of the research and the companies as a whole. But I think that in this case, it's the basic chemical engineering. So get a diverse force of chemical engineers on the job, and then set them to improving the processes. But the major thing, I think, is the acceptance that we've got a problem and that we need to actually get on with it, which I think we've been saying for the last 10-15 years. So a diverse set of people pushing for decarbonisation is an excellent thing, and it's interesting that nowadays we seem to have much more of a broad-based coalition of people that have accepted that decarbonisation is important. Well, I mean, we had one until maybe the most recent change of government.
Yes, and we're going to come back to that importance of government, but what you're referring to, Paul, for those who aren't following the UK change in government, is which I'm sure everybody is the fact that we used to have a government that was extremely keen on net zero by 2050, and now we don't. We have a government that's interested in other things. So, by
all accounts, blocking the king from going and giving a talk.
For example, in Egypt, yes. Leon, let me ask you. You really brought across how the industry that you're talking about is one that is profligate, really, in its waste. That everything is so importantly valuable that for it to use, doesn't matter that you chuck half of it away, and because its shelf life has expired. Or so. Do you find that different hospitals or different users have different wastes? So have you got any link to the people involved in this? That some of them are better and more careful than others?
Yeah, absolutely. I mean, I think that's a great question. And just on the government, our government's gone the other way a little bit. We've got a bit more serious about emissions. Long way to go still.
Because I think government is the key question in this. But let's deal with the employees that you think you need to have.
Yeah, I think it's about that mindset, kind of what Paul touched on, because it affects every bit. And the earlier you start the thinking, the better it gets. Sometimes you see products or designs get to final prototype stage before anyone goes, oh, let's think about how we can make this a bit more sustainable. But actually, that decision should have been made way earlier, right? And it involves not just the kind of the materials designer, but involves the engineers who are going to build it, and the people are going to register it, and thinking about the end user. There's very significant thought that needs to go in earlier. And I'll probably just also add, I think the cost question that we're probably going to touch on is one of the big ones. Right? What are the economic drivers for the real sustainability? How do we ground it in dollars?
And Fang, on the same question about people, I imagine people want to come and do research in your research team, because they're passionate about how great this might be for the planet and how we might improve all of these things. Do you spend any time saying, by the way, you do need to kind of sell this? You need, people don't want to pay more for anything at all. They want it quicker. They want it. They don't really care. How much is that kind of societal acceptance of your research? How much do you find your PhD students, for example, are really focused on the public acceptance of what they're doing?
I'd be to be very honest with you. I mean, at the moment, we still focus on we're still in this little box of a lot of research is efficiency driven. You consider, because you kind of design a material, I think we really think, because at the moment the stage is you educate students to try to get the best material design by machine learning, and to say, okay, this particular design give you the best efficiency for whatever, like harvesting, water oxidation, all these applications we are working on. But we don't, I mean, even myself, we are in this transition mode to have this holistic way, okay, to make this particular material. Can we choose some earth abundant elements? I mean, from the beginning to think whether even this is a magic material, but if the whole process is very toxic, very environmentally not friendly, we probably have to rethink of it. And all this holistic thinking of Circle isn't there at the moment. We are, like the departments, I mean, Paul in chem engineering, I'm not sure, do you have the new modules coming on? We are trying to have new modules coming on to educate next generation about sustainability, about the circular of the materials, including the generation material and the process. So you can't just looking at how wonderful graphing it is. We need to think the production process to form a cycle. So this is, I think, for the next generation's education, all this holistic view need to be implanted. So naturally they can think in that way. But in my generation, I probably still focus on a lot of proposal writing. You really need to think how efficient this can enhance the device performance and stuff like that.
Yeah.
Then we will end up like plastic. It was wonderful material, right, in 1970s, and then now we have to clean up.
Yeah. Paul, I think I'm going to come, Joe, sorry, I think I'm going to come to you on this. And isn't there also a reaction from the market that you come in with all this sort of goody two-shoes stuff about, oh, it's lovely and sustainable, and then the people who are selling the old stuff, the old rubbish stuff, they've got scraped knuckles. Their life depends on continuing to sell that old stuff. Joe, do you not find that they say that the stuff you make, oh, it's not as good quality, it's full of rubbish or something, it's all just recycled, it's not up to it? Do you get that sort of resistance from the embedded suppliers?
You definitely see a variance. So I would say petrochemical companies are very much engaged. They are looking to increase the amount of feedstock that they get from recycled sources. There is, often you see publications in the media about companies who claim to have proven a circular economy system by recycling plastic, sending it to a refinery. You then find out that it was, a teaspoon equivalent of recycled material, which was why it could be happily processed in the existing system, because it's such small quantities that it didn't make a difference. And as we scale up, contamination from recycled sources or lower grade material, as you point out, will become a bigger problem than it is when you're at relatively low volumes. But certainly within, the plastic supply chain, a number of people are engaged and are interested in increasing the amount of recycled content. I would say that more needs to be done to enable that to happen. Yeah.
Yeah, but Leon, you said how difficult it was to change a material in some particular process, maybe because of the bio nature of what you're doing. Is that partly the resistance of the previous people who are making it, or is it not? Is everybody's keen to have it changed? They're just very nervous that it might kill someone.
Yeah, I think it's that keen to have it changed, but the previous systems are so well proven and done that you can't easily change it, and the regulation on top, right? We use a whole lot of plastic in my workplace. We have 18 plastic injection molding machines running almost 24/7. Right? If we were to use a recycled grade of polyethylene, right, it would raise all these complexities for the regulation and delivery. Right? It becomes more complex just because the process is different in some way. We'd have to take the step to prove it somehow that it's suitable, and that's the real challenge.
Yeah, so the status quo has a real inertia.
Absolutely.
So Paul, there's a question here from Michael Hancock, Paul, about the value of the International Standards Organization, ISO, in kind of cutting through all this and saying, well, my polyethylene is ISO 73007 accredited or something. Is that the way through it, that you just put a stamp? How do we get through this? The stuff you make is this new concrete with low carbon, that's not as good as the old concrete. How do you get through that?
Yeah, very much so. In fact, there's some work going on at the moment to look at whether or not existing standards can be changed to allow such things. So yeah, ISO, as I say, ISO and other standards organization, or a number of different standards organizations, need to get together and work out a global standard. But sometimes these things take a very long time to do, so there needs to be a fire lit under them, I guess.
Have any of the four of you, have you been involved in setting standards, or know folk would do? Are they the right sort of mentality people to drive the change we need, or are they also got inertia? Any comments on standards, the way that we can use them?
I know that Progressive has been doing some work on standards for CO2 transport.
Yeah, we're quite
fiery go-getters.
Yeah, we're quite active in CO2 transport standards, as well as kind of hydrogen standards. As I think Paul mentioned it in his talk, that the individuals involved are engaged and are really keen to create a set of standards that can be used to develop the industry. However, there are inevitably an element of conservatism in setting those standards that make it quite difficult. And there are good reasons for that, obviously, with respect to health and safety, and that being the most important factor.
Okay, it is an interesting one, and I had a very limited amount involved with standards organizations. And forgive me, because this is on the internet and people can hear what I say, but the need for them to be correct and involve all the views and be sort of thought through before they come out with something means that they're intrinsically very, very slow. They're not dynamic change, or in my personal view. So to sort of say, oh well, we'll leave it to the British Standards Institute to do something, with huge respect to them, I think they more or less come along afterwards, don't they, and ratify what somebody else might have come up with. So anyway, that was perhaps an unfortunate comment, probably. Let me come to a little comment that Paul made earlier on, Joe, about if only we had infinite amounts of hydrogen. And I know you're of green hydrogen cheaply. Could you just give us a view about whether that is going to be the sort of the cavalry coming over the hill here that we're after, that we can see a way to new low cost, low environmental impact materials becoming available that then get through a whole range of different processes?
Yeah, so I think Paul mentioned kind of green hydrogen relative cost to blue hydrogen. Some of that picture on cost differential is changing with current gas market prices and electricity prices, and whether you can decouple those two things. But probably most important is to say that at the moment, hydrogen is more expensive than natural gas. We're all aware of impact of inflation and cost of living, and just replacing your fuel source with a more expensive fuel source will make that much worse. Governments, at least within Europe, are primarily managing that with a kind of hydrogen support model, where you sell hydrogen to end users at the same price as natural gas, and the governments basically cover the cost of difference to the producers in the short term. That's obviously, helps to get the technology off the ground and commercially demonstrated and the network infrastructure developed. But longer term, we obviously need to try and achieve cost parity with those alternative fuel source generations. And the big thing it always comes back to is, unless we have a true cost of carbon to society within the process, so an appropriate price for CO2 emissions, it's very difficult to ever achieve cost parity between hydrocarbon sources and alternative fuels. So there's definitely, government and regulation are the most important factors in putting in place a kind of a carbon economy and support to infrastructure getting off the ground.
And Fang, you must get involved internationally with your own research. Do you find that certain countries are kind of picking up on that they say this is something that we should do? Could we? Are there? If Tony Blair was still with us, he would like to say that the Climate Change Act and the UK was a leader in trying to do. Are there countries that you see that are leading in this, and that are really making sure that even though the stuff we do is expensive and it's difficult at the moment, you do get these sort of national commitments that are very important?
Yeah, I think so. Because for the North area, I think New Zealand did extremely well. There's quite a few big, relatively big companies based in New Zealand, and also graphene as well. I mean, graphene, the production, UK, US, China is leading at the moment, but I mean, from my perspective, I feel that the government is basically at the top of the food chain. We are researchers, it's at the bottom of the food chain. We kind of not really policymakers, and if the policymakers are really after it, then the research, there's capacity there to move this quicker. But if the government is not going that way or not emphasizing that way, then the researchers it's slower in a sense.
So, Leon, why do you think your government has gone more towards sustainability in the last year or two?
Well, we changed governments, and there's a fairly strong green movement in Australia, such that I think they won either 4 or 7 seats in the lower house of Parliament, and they're doing pretty well. They're pushing hard for real green policies. That said, I think it's really difficult in the Australian context, because we're really good at digging things up and sending them away. That's one of our specialities. Yeah, we're really, really good at it. We can dig up lots and lots of stuff and send it anywhere. We're less good at adding value using real sustainable processes. I think that the hydrogen one is one that Australia will be working more on, but it's a very long road. Paul's example about blue hydrogen, green hydrogen. 97% of Australia's hydrogen comes from fossil fuels, and the pathway to making that sustainable is difficult. But I think putting in place price guides to it, making it more difficult to be wasteful and more lucrative to be sustainable is critical. Right? I'm a big fan of economic drivers for sustainability, and I think we've got to pull those levers much more vigorously than we are at present.
All right. Well, I've got a final question for all of you so that we finish on time, and I was going to ask it in a very negative way, because it's something about, well, what is the main thing that's stopping these changes occurring? But I'm delighted that Adam Duckett has just come up on the questions and asked it in a much more positive way, and I'll just read it out. What do you think are the key opportunities for chemical engineers in order to make this happen and improve the sustainability materials? Where should the chemical engineering community be putting its focus? And I'll start with you, Paul. What's the one thing that you would, in your dreams, you would happen tomorrow type thing?
Well, I think I'd say that is basic chemical engineering. I mean, you know, the application of chemical engineering to the massive number of problems that we have, you know, including life cycle analysis, that's very important, but keep going, keep being chemical engineers, and keep looking at the systems that need changing and looking at how to actually decarbonize them. I think what we need is a big dose of chemical engineering, and we need money from government, industry, people to actually effect these changes. And people will need to understand that, you know, some things may get more expensive in the short term. Some things may get cheaper in the long term because we do R&D. I mean, that's what's happened with everything in the past. You know, we need to do the R&D, and then things will get cheaper.
It sounds a bit like a party conference. Everybody's nodding their head. Leon, I'll come to you. More chemical engineers, that'll solve it.
More chemical engineers and the money drivers to make it happen. Yeah, I think chemical engineers. I mean, chemical engineers are the best because we think systems, and we think big picture, and we think at the level of detail that's deep enough to be meaningful, but big enough to be practical. So, yeah.
Thanks. Well, Joe, just in case you were exactly the same thing. Let me try and the contrary argument. We need better communicating chemical term increase in pain or cost or difficulty is actually worthwhile. We need better communicators, don't we?
Yeah, lost you a little bit there, Colin. Don't know if that was me, but caught the end of it on better communicators. So I think the main thing from the perspective of plastic recycling.
That's right. We don't need more chemical engineers. We need better salespeople.
I think the main thing on plastic recycling is that the chemistry has largely been demonstrated. So getting out there with that message that there is a technology viable solution for the vast majority of current polymers out there to be recycled is really important, and getting that message out there, and then the subsequent political framework in regulation and financial support and changing investment from current kind of virgin polymer production routes to recycled polymer production routes can be done. The technology exists, the chemical engineers are there, and let's get on with it.
And Fang, let me be slightly controversial. The stuff you're producing here is real grey goo. We ought to be frightened of all of this small stuff. It'll cause us all sorts of problems. How on earth do you deal with the fact that somebody at some point might say, "Oh, we shouldn't be going down this road"? How do you get the support for what you're doing?
It's a tough question. Yeah, so nanotechnology is always, especially, it's not really welcoming in healthcare, because people are worried about nanoparticles, and especially recycling is very, very difficult. But for graphene, I would say, because it's naturally carbon, so this recycling of graphene, which there's no need for that. So if branding into composite materials, it's carbon. So I don't think there is a risk there of putting graphene into a lot of things. For MOF, it's a slightly different scenario, because once you branding nanomorphs into a lot of stuff and then trying to recycle and separate them, that's very hard. That's a good question to think about it. And to answer your first question, I would think we really need to educate next generation chemical engineers with the sustainability in mind. So some courses need to be implanted into the undergraduate study, to have a very specific course to talk about sustainability from beginning to end. So they be naturally, like inherent, have the capability of thinking sustainably than our old generation, I would imagine. So that's my view about what's coming on. Yeah.
Well, brilliant. Thank you very much, Fang, Leon, Paul, and Joe, for being so open and constructive. I think you've ended on a very nice positive note there, Fang, that good chemical engineers are indeed a key part of the solution to these issues for reducing the impact of our use of materials in the world. So thank you to all of you. Thank you very much to those of you who put questions in and to joining us today. And that's it for today. Thank you very much.
Thank you. Bye-bye.
Bye.
Thank you.